In this video, we're going to work through a couple of sample calculations using the equation relating root mean squared speed of a gas to molar mass and temperature. So in the last video, we derived these equations here, which are actually just different ways to write the same equation, showing the relationship between molar mass, the capital M, and temperature in Kelvin. And I pointed out at the end of the last video that in order for your units to work out, you're going to have your molar mass in kilograms per mole. Now, if you're writing out your units like you're supposed to, then you would catch that every single time you worked through anyway. So the best way to start any calculation is going to be by organizing what it is that you know. So in this case, we know that we are being asked to calculate the root mean squared speed. We know that the temperature is 20 degrees Celsius, and we can therefore convert that to Kelvin by adding 273.15. So that gives us a temperature of 298.15 Kelvin. And we know that we are working with nitrogen gas, which means that the molar mass is going to be equal to twice 14.0067 grams per mole, or therefore 28.0134 grams per mole. And then when we look at our formula sheet for equations involving those three terms, the two that we know and the one that we're solving for, we would get back to one of the equations written at the top of the screen. So we would have root mean squared speed equal to the square root of 3RT divided by molar mass. So if I go ahead and plug in numbers, R is 8.314462 joules per mole Kelvin. The temperature is 298.15 Kelvin. My molar mass, as calculated over there, was 28.0134 grams per mole. My kelvins cancel, my moles cancel, joules and grams do not, but I know that 1 joule is equal to 1 kilogram meters squared per second squared. So I can put that in as a conversion factor. And now my joules will cancel, but grams and kilograms don't cancel. This is why I said it would be easier to just convert your molar mass to kilograms per mole in the first place. But if you forgot to do that, you can do so now, simply by recognizing that there are 1,000 grams in 1 kilogram. And so the grams cancel and the kilograms cancel, and I'm now left with units of square root of meters squared per second squared, or meters per second. Put the other numbers into the calculator, and we should get a final answer of 511 meters per second as the root mean squared speed for molecules of nitrogen at 20 degrees Celsius. I'm sure somebody out there is wondering why I only answered with 3 significant figures. That seems incompatible with anything else, but it's not. If we zoom in on our temperature here, 20 degrees Celsius plus 273.15 gives you 298 with no decimal places attached as the significant figures. So my temperature actually only has 3 significant figures in it. I don't want to prematurely round, so I keep the 0.15 in my calculator, but that's where my significant figures come from. In the next question, we're told that our sample is starting off at 0.00 degrees C, which is 273.15 Kelvin, and we want to know what temperature we need to heat it up to increase the root mean squared speed of our atoms by 10%. And so we have one temperature, we're solving for another temperature. Because we are talking about helium, we know that our molar mass will be equal to 4.0026 grams per mole, or 0.00400026 kilograms per mole. And there are different approaches to this calculation, and some of them use the molar mass, and if you take that approach, that's completely fine. I'm not actually going to need to use the molar mass in my approach to this question. I've also been asked about increasing the root mean squared speed. I'm not given an initial speed, and I'm not given a final speed, but I know what the relationship between the two speeds is. So if I say that I have speed 1 is whatever speed 1 is, then speed 2 is going to be equal to 10% more than speed 1. So it's going to be 110.0% of speed 1, or more easily, 1.100 speed 1. Now you could take your molar mass of helium and your temperature and use the equation that we used on the last page, the mv squared equals 3RT, and solve for the root mean squared speed. That would be completely fine. You can do that, solve for V1, and then use V1 to solve for V2, and that's fine. Works great. I'm going to answer this question without directly using the molar mass because of the fact that I could have actually been asked this question without being given the molar mass. The molar mass makes the second approach viable. So if I did not have molar mass, then what I would need to do is I would need to recognize that the molar mass times the first speed is going to be equal to 3 times the ideal gas constant times the first temperature, and the molar mass times the second speed is going to be equal to 3 times the ideal gas constant times the second temperature. And I can rearrange each of these equations such that I group together the terms that are changing on one side, and I group together all of my constants on the other side. So since the first speed squared divided by the first temperature is equal to 3R over m, and the second speed squared divided by the second temperature is equal to 3R over m, it's therefore safe for us to say that the first speed squared divided by the first temperature is equal to the second speed squared divided by the second temperature. And now we have numbers for everything. So all we need to do is recognize that the second speed is equal to 1.100 times the first speed, square all of that, and therefore we have V1 squared over T1 is equal to 1.210 V1 squared over T2. The V1 squareds cancel, and therefore 1 over T1 is equal to 1.210 over T2, and therefore T2 is equal to 1.210 T1, and I can plug some numbers in, and that was 273.15 Kelvin, and therefore my final answer is 330.5 Kelvin, or 57.4 degrees C. And the values that we've calculated here are consistent with the values that we measure experimentally, and that demonstrates that helium, therefore, under these conditions,